Okay, let's talk about the derivation of an equation for the induced EMF in an AC generator. You know, in our previous videos, we described the EMF that is induced in a coil in an AC generator. So now we're going to try to derive an equation for it. So derivation of an equation for the induced EMF. Induced EMF in an AC generator. So now let's consider a coil, a rectangular coil of area. Let's consider a rectangular coil of area A meter square, placed in a magnetic field of strength. In a magnetic field of strength B. Now, okay, as can be seen below. So let's consider a coil. Let's consider a coil of area A meter square. Place the magnetic field of strength B, as can be seen below. So we have N. We also have S here. So of course the magnetic flux goes this way, which is magnetic lines of force. So we have a coil, a rectangular coil, placed in this field in this way. Now, if this rectangular coil moves, begins to turn, such that the normal to the coil makes an angle theta with the magnetic field, with magnetic flux. That means this magnetic flux here, phi, will be given by the dot product. Phi is given by the dot product of the area and the magnetic field. And the dot product of that is going to be AB cos theta. Let's call this equation 1. Now, if this coil has n number of turns, if coil has n number of turns, n turns, that means this equation 1 becomes phi is equal to NAB cos theta. Let's call this equation 2. Now, according to Faraday's law of electromagnetic induction, which states that the EMF, the induced EMF in a conductor in a magnetic field, is directly proportional to the time rate of change of the flux, which means E is equal to delta phi delta T. Call this equation 3. So this is what Faraday's law of electromagnetic induction states, that when you have a coil in a magnetic field turning in a magnetic field, there will be an induced EMF into it, the magnitude of which is proportional to the change of the flux. Now, also in Lenz's law, Lenz also gives the direction of this induced EMF, and so it is equal to minus delta phi delta t. Equation 4. So what we see in this equation 4 is a combination of both the Faraday's law of electromagnetic induction and the Lenz's law. You see. So, but from here, from equation 1, you can see that phi is equal to AB cos theta. That means you can remove phi from here and put AB cos theta there. So equation 4 now becomes E is equal to minus d dt n AB cos theta. Of course, this one can come forward, and so we have E is equal to minus NAB d dt cos theta. Now, but you know that omega is equal to theta over t, which means that theta is equal to omega t. Why? Because when you do a cross multiplication, this multiplied and then this will stand alone, which gives us this. So now we are going to put this in place of theta in this equation here, and so we have E is equal to minus NAB d dt cos omega t. You see? So now we have the whole of this. We have to first find how we can differentiate this. So here we can see that y is equal to, this is differential equation, y is equal to, okay, sorry, let's say, let u be equal to omega t. We are trying to use differentiation of function of a function. So that means that y will be equal to cos u. Now, by using function of a function, or what they call the chain rule. By using function of a function, we know that dy dt is equal to dy du dt. Now, what is dy du? So if y is equal to cos u, that means dy du will be equal to minus sine u. We'll keep this one aside for a while. Okay, let's call this what equation now? Let's call this equation 5. Also, if u is equal to omega t, it means that du dt will be what? Omega. So that means that dy dt will now become omega minus omega sine u. But remember that u is equal to omega t. That means we put it back in here. So the y dt will now become minus omega sine omega t. This is equation 6. So we're now going to put equation 6 back into this equation here. Oh, unfortunately, okay, let me label it. So this is equation 4, here will be 5, here will be 6, and here will be 7. So now putting 7 in 5, we have, now we're going to put this equation here into this place. So we have that, we have E is equal to, which is the induced EMF, is equal to minus NAB where N is the number of turns, A is the area of the coil, and then B is the magnetic field strength or magnetic field intensity. Then multiplied by minus omega sine omega t. Now this minus, when you multiply them, it goes away. So we have E is equal to NAB omega sine omega t. Now, if omega t is equal to pi over 2 radian, which is 90 degrees, sine 90 degrees is 1, right? So that means this equation here, equation 8, becomes E is equal to, which is the induced EMF, it becomes E naught, which is NAB omega. We call this one equation 9. So when we put equation 9 into equation 8, we have E is equal to E naught sine omega t. So this is equation 10. Because in place of the whole of this, we can put E there, and this becomes like this. So now equation 10 gives the induced EMF in an AC generator. So that's what it is. This is the equation here for the induced EMF in an AC generator. So that's the recap. So the topic today is a derivation of an equation. We want to know what the equation for the induced EMF in an AC generator would be. So we say we consider a coil placed in a magnetic field of field strength B. So this coil here is placed here. Now, if this coil begins to rotate in such a way that the normal to the coil makes an angle theta with the magnetic field, with the magnetic flux, that means the magnetic flux phi will give us phi is equal to, it will be the dot product of both the area of this rectangular coil and the magnetic field strength, then cos theta, and this is what it is. Now, if the coil has n turns, n number of turns, that means phi becomes NAB cos theta. Now remember from your two laws of electromagnetic induction, that's the Faraday's law and the Lenz's law. Remember, the Faraday's law gives the magnitude of the induced EMF, while the Lenz's law gives the direction. And the Faraday's law of electromagnetic induction states that when you have a coil placed in a magnetic field, the induced EMF into that coil is directly proportional to the rate of change of magnetic flux, which is the rate of change, how quickly this coil is cut in the magnetic field lines. And that's what you have in this equation. E is equal to delta phi over delta t. It's time dependent. Now, E here, which is the induced EMF, becomes, okay, now when you factor in Lenz's law, Lenz's law states that the direction of induced EMF or the induced current is such that it's opposed to the motion creating it, inducing the current. So that's why we have a negative sign here. Now, if you remove phi and put the equation for it in this equation 4, we have E is equal to minus d delta t NAB cos theta. And of course, you can bring this one out here since they're a constant. So we have this here. Now, but remember that theta is equal to omega t. That means we remove theta and can put omega t inside. We want to bring out a time-dependent equation. So we have E is equal to minus, that is the induced EMF is equal to minus NAB d dt cos omega t. Now we say let U be equal to omega t, and that means Y is going to be equal to because this is a differential equation now. Y is going to be equal to cos theta. Now, by using the function of a function to differentiate this equation here, function of a function, we have dy dt is equal to dy du dt. So if y equals cos theta, that means dy du will become, when you differentiate it, you get minus sine theta. And if u is equal to omega t, that means du dt will give us, you differentiate this with respect to t, and then the t will go off. So we have our omega. So dy dt now is going to become, when you multiply du dt and dy du. So when you do that, we get minus omega sine u. But remember that u is equal to omega t, which means we can remove this and then put back omega t inside. And that means that dy dt becomes minus omega sine omega t, equation 7. Now, when we put this equation 7 into this equation 5, you remove the whole of this differential equation and then put this one inside. So we're going to get E, which is the induced EMF, will be equal to minus NAB bracket minus omega sine omega t. Now, these negative signs, when you multiply them, will have to go away, and that means we have this left. This one is basically the same thing as this. It's just that it doesn't have the minus signs to it. Now, let's imagine that omega t becomes pi 2 radian. Now remember, we have the induced EMF is maximum when the phase angle is 90 degrees or pi over 2 radian. So when that is the case, it means sine omega t becomes 1, and that's when the induced EMF will be maximum and to be equal to this one only. So now in this equation here, so since the whole of this means maximum EMF induced, we can remove it and then put E naught there. So that equation now becomes E is equal to E naught sine omega t. So this equation here, equation 10, gives us the induced EMF in an AC generator.